All right. Welcome to Recitation 2 for MAE 242, Fluid Mechanics. So this first problem, we're going to be dealing with a manometer. And we want to find the difference in pressure PB minus PA between the centers A and B of the pipes which are filled with water. The mercury in the inclined tube manometer has level shown, takes specific gravity S of Hg equal to 13.55. All right, like I was saying before, we want to use this specific gravity ratio to determine the density of mercury. So I always like writing S of some substance X is equal to its density over some reference density. And then you can throw on your gravity terms. And this reference density, we always like using water because we always know the density of water. So in this case, we're going to use this to find gamma, because gamma your specific weight is equal to rho times G. So rho of water, or gamma of water, equals rho of water, density of water, which in this case we just like to use 1,000, times gravity, which is 9.81. And so this will equal 9810 newtons per cubic meter. And now, since it's just a ratio, this is really easy. Just multiply this by 13.55. That should be a really big number, which is 132,925.5. Newtons per cubic meter. All right, so we've got that now. We've got pretty much everything we really need to get started on this. And now, since we're taking a pressure difference between points B and point A, we don't really care about what the actual pressure here is. It could be 1,000,000 pascals for all we care. It's fine. So just for the sake of argument, we're going to call PA equal to 0. And now recall your standard point-to-point pressure equation as P at some point, I'll call I, equals your initial pressure wherever you're starting plus rho GH. And in this case, that rho GH can be replaced with gamma. It's the same thing. In practice, I like to just use rho GH instead of gamma because it's just one less variable I always have to remember. But for this, we do that. So this one's pretty easy. So start off, we know the pressure A is 0. So to do these, you find your points of interest, and obviously our pre-prescribed points of interest are points A and B. And then for the other points, you want to find each spot where the fluid changes. So C changes from water to mercury, B changes from mercury back to water. And we want to mark those as our other points. So now we're ready to get going. So to find the pressure point C, we go PC equals your point before it, point A, plus gamma of water times the height of the column, the vertical height of the column. We don't care about the side-to-side action, we just care about the vertical. So this equals 0 plus, and I always like to, obviously gravity is going down that way. And when I'm doing these, you'll see some professors have different sign conventions for it, but I always like to remember if I'm going with the flow of gravity, I add the plus rho GH or plus gamma H. So 9810 times the height of the column, 0.1 meters. So we'll have PC equal to 981 pascals in this case. Okay, so now you're good. So we found point C. Now for point D, we don't care about, we just care about the height difference between point C and point D. We do not care about anything that goes on below here. This angle is totally irrelevant also, it's just here to throw you off. We don't care about this angle, we just care, we can just do basic subtraction and find the height difference between these two. So let's do that. So point D equals point C, which is 981 plus gamma of mercury now. Is that really big number? 132,925. Times the height of the vertical height of the column, 0.15 meters. this is a significantly larger number, which is 20,919 pretty much. .825 pascals. All right. So now we're going back to water for this last one, and we're just going straight up. So we'll be actually, I'm just going to move over here because this is almost what is it. So now for PB, you have PD. Now we're going up, so we're going to subtract the amount of water times H. So we have PB equals that. Minus 98 times just 0.25, so straight up. Okay, so we get PB equals 18,467 pascals. All right, so now we found the pressure at point B, and so now we just want to find the difference between point A and point B, and since we call point A our reference pressure is 0, it's just super easy. So delta P, you'll see it written as like delta P a lot. Equals PB minus PA, which we already said PA is 0, equals 18.467 kPa, kilopascals. Boom, all right. Any questions there? These are usually pretty easy. If you see this on exam, you should be like, hey, sweet. Manometer problems are nice and easy. What's up?
Are we always going to assume that like the initial pressure is 0?
Unless there's like, it's explicitly stated there's an overpressure, or like the problem statement says like calculate things in absolute pressures, then you would have to factor it in. But usually if you're just finding a pressure difference, you don't really care about what your initial pressure is, because that's your reference. That's what you're going to be subtracting at the end anyway, so it'll just wash out at the end. If you really wanted to, you could carry that whole PA through the whole problem. It'd get you the same number though, so in practice I always just call that 0 and move on with my life. So anyway, any questions with that? Those are usually pretty easy. The second problem is very important, so it'll be a little more involved, but it'll be good. You guys, like I said, you guys have a leg up on the other classes since you already know what's going on with this next one. Yeah, and we'll post this key tonight at some point. If we don't, just email me and I'll do it myself. But yeah, here's all that. And yeah, a lot of times you'll see like, answer keys and stuff. We'll just chain all the points together like that. You could totally do that. When you're still getting the hang of them though, I would say just go point to point and then add them all together at the end. It's fine, it's the same thing. All right, anyway, so for problem 2, have you guys seen something that looks vaguely like this? Yeah? Yeah? Here, let me adjust it a little bit. All right, cool. So we've got a submerged gate underwater. We're dealing with forces on a submerged object. So the gate in figure 1, I guess, is 5 feet wide. It's hinged at point B and rests against a smooth wall at point A. The force on the gate due to seawater pressure, the horizontal force P exerted by the wall at point A, and see the reactions at the hinge B. So first over here, I'm just going to draw a little free body diagram of the stuff we really want to find. So on this gate, we've got point B down here, and up to wall, point A. And then on point A, we've got this force, we're calling it P from the wall. And then we've got some water, force of seawater, F, acting there. And remember, pressures are always perpendicular and normal to whatever surface they're acting on. And also, remember, and this will be very important later if you guys have forgotten, here would be like the centroid of the gate right here, I'll call that C. The force acts slightly below the centroid because it's a distributed load, and so the actual point of concentration is slightly below the midpoint of whatever object you're dealing with. Now we've got our reaction forces, By and Bx. Okay, now we're ready to start going. So for part A, it's pretty easy just to compute the force. You just want to find the actual height of this centroid, just from basic math. Since this is 6 feet high, the centroid would be 3 feet high right here. So 15 minus 3, I'll say HC equals 12 feet below the water. And this kind of sucks because we're using like pound per cubic foot. We're using British units. I always prefer SI, but it's all the same. So now find the pressure, we go pressure equals, in this case, this is our gamma. That's our GH, or our rho G term. So equals gamma times HC. So in this case, we have P equals 64 times 12. So our pressure equals, should be like, I'll tell you, someone do that math for me. Oh, never mind, I got it. 768. And that's PSF, pounds per square foot. So now to find the force acting on the gate, you just multiply it by the area of the gate. So, F equals P times A. So F in this case equals 768. And I'll just tell you, if you don't believe me, go do the Pythagorean theorem. This is 10 feet. 64 plus 36, 100, square root of 10. We have 10 times its 5y into the page. So we've got the force on the gate itself is 38,400 pounds. All right, so there's part A done. And at the very least, it's just kind of a cool fact, like that's only 12 feet underwater and it's 38,000 pounds. It's pretty crazy. Water's really heavy. All right, so there's that. Now, oh yeah, what's up?
Wait, how did you know it was 12 feet?
Oh, because so the centroid would be like right here, because it's just halfway up. And if that's 6, so this is gonna be 3 right here. And then just 15 minus 3 to find the height underneath the water.
Oh, okay.
Yep. Yeah. Anyway. Yeah, what's up?
Can you explain how the centroid is, or sorry, but like the force isn't acting at the centroid? Because like when we do distributed load in like statics or whatever, it's directly in the middle.
Yeah, because so just for reference, like I'm going to explain it in terms of using this wall. So all water pressure is, since we're assuming density is constant, it's a triangular distributed load, So we've got forces are like that. And so to calculate the total overall pressure, it's half of a square. And so like it would, you just calculate it like at right there. But where this force is acting is going to be slightly lower because it's a distributed load. But so for like, if it's just a straight up wall, you can actually just use your mechanics knowledge to use that. But since this is going to be curved, you have to do a couple extra steps because it's not just, like for this, it would be 2/3 of the way from the end, or 1/3 the other way. But since this is curved, it's tilted, you have to do some extra math. But yeah, that's the physical basis for it.
Yeah, I forgot that it changed with the height, so that makes sense.
Yep. Yeah, it's definitely something to keep in mind. A lot of people get stuff on that. But anyway, okay. So now to find the horizontal force P acting on the gate, we have to take a bunch of moments about the gate. And in order to do that, we need to know where this force is actually acting. And like I was saying, it acts slightly below the centroid. So to do that, I'm going to come over here and redraw this whole thing. So we've got the water over here, and we've got the wall, and we've got our gate. And I'm going to extend the end of this gate up like that, right? And then here's our centroid C. And then I'm going to call a new constant y bar. And that's defined from the height of from the height of the surface of the water down to the centroid, like diagonal, tilted on its axis at this angle theta. And this angle theta, I'll just tell you, it's 36.87 degrees. Okay. And now, since we still know this height is 12 feet, okay, and then using other triangle math and stuff, you know, using these angles as well, we can do all sorts of stuff. So, we know this y bar should be like 20 feet. This y bar equals hc over sine theta. That's just for trigonometry, you can go into that stuff if you really want. Anyway, you get y bar equals about 20 feet. It's like 19.999, blah, 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 whatever. Okay, so cool. Now we've tilted this on its axis, so that's good. And so now we've got it in terms of the actual plane that this is sitting on. So now we want to find this little tiny distance, this HCOP, and we call this little length L right here. That defines the distance we're moving down. And the way you find L, it actually stems from like the definition of, you know, like physically what we're doing is we're taking moments about the gate in terms of the height of what it is underneath the water. And with that, there comes to be like moments of inertia involved in it. And I'm sure we went over the derivation with you guys very in depth. I'm not gonna do that here. But the equation for it turns out to be pretty simple. You just have to remember your moments of inertia equation. But it's, so this length L is I x, the moment of inertia about the x-axis, over y bar times the area of the gate. And so just cleaning this up, it'll be, you know, IXX in this case, since it's a rectangle, is 1/12 base times height cubed, which you should all know and love from all of your mechanics classes. So we've got 1/12 over y bar times base times height. I'm just gonna clean this up. Let's do 2. So L is 1/12 times 1/20 times the height, which is, and we're talking about the height not in terms of from the ground up, but from the axis we're tilted on. So this height would be 10 cubed, or 10 squared, sorry. So 100. So we get L ends up being 0.416 feet. And this is the distance along the plane, along this tilted axis. So this will be shifted down just like that. So now we're pretty much ready to go. We know where that force is acting. It's acting 0.416 feet below the centroid along the axis of the gate. So I'm going to redraw this a little bigger with all of our new information. So we've got Vy, Ex, gate, okay, P, got our angle, theta, and then got our force acting right here. And so this distance so for part B, we want to find the horizontal force. And so to do that, obviously we have too many unknowns, just do like sum of forces in X and Y direction. So we're going to take one about point B. So good. That direction. So we've got this length right here. This will be 5 minus L for this length right here. And then this distance for P is obviously just 10 feet. Okay. So for this one, and we don't need to do any cosine sine manipulation with F, since it's already perfectly perpendicular to that, and we're doing everything in terms of this theta. So we've got F times 5 minus L, and that will be negative, this is going in the opposite direction, and plus P, and this will be cosine sine theta times 10. All right, now just do some basic math. You guys know how to do this part. Everything after like all of this stuff, this is just all mechanics review. If you can get to this point, you guys are good. After this, just go back, look at your mechanics notes, something like that. But, yeah, keep them going. Just plug in the numbers, do some calculator math. It'll be cool. Because we know F, we already know F is 38,400. So plug everything in, end up getting that P equals 29,337. This is pounds again. Cool, okay. So now that was the hardest part. After that, everything else is pretty easy. Now, since we do know P, we can just do sum of moments. So just go back. Let's do sum of forces about X is 0 equals F cosine theta minus P, and oh yeah, plus BX. So it's 490. Okay. So now, once again, just plug in numbers. BX ends up equaling 6296. There's that. Now, same thing for BY. Some force about Y is 0. And we obviously don't care about like force of gravity. We're neglecting gravity for like the normal reactions, stuff like that. We don't care. F, negative F sine theta plus BY. Obviously, there's no component of P acting in the vertical direction. So plug in, you get BY equals 38,719 pounds again. Cool. All right. Now we've got everything. Should be good to go. Any questions on that? Yeah, the hardest part for this is just manipulating your mind and shifting your thinking into saying, all right, I've got to tilt this on its axis and take this Y bar, extend this out, get it all in terms of the height below the level, the sea level along the plane of the gate. It's kind of hard for people to wrap their mind around. But after you get that down, yeah, it's just all review. It's just all mechanics review that you've been doing for the past like 2 or 3 semesters, or however long you mechanical engineers do your stuff for, I don't know. But yeah. These are usually pretty involved, and I can almost guarantee there will be one like this on your exam. So if you're really confused, shoot me an email and we can make something happen, or just get really good at practicing these. But any questions before I move on to the last one? Cool. All right, this last one's really fast, but there's a couple of really important concepts that will be good to know on it. And has he started talking about forces on curved surfaces? Oh, okay. Well, it's not that tough. There's just one little extra tweak you have to do, but you'll find you'll figure it out. It's not bad. All right. Here's all the math for it and everything. Not too bad, not too bad. Yeah, and also sometimes you'll see it written as like YP equals Y bar plus that. I don't really like that because you end up just carrying this 20 term along with, which you don't really need. You just want to find how far it's going below. Like, you just end up finding L anyway, you end up subtracting it out, so just cut out the middleman and just do the basic math for it. But whatever. All right, now, so for problem 3, we've got this air. Oh yeah, in this case, like remember for the manometer, what's up?
I got one question.
Yeah, what's up?
Are you guys gonna post this with any solutions to the, cause like on the first question, I like how it showed that you could string it along, but,
Yeah.
I would do it piecewise at first, but it's nice to see that.
Yeah,
Have it written down.
yeah, we should have these out tonight at some point after the last recitation is done for today. If not, just email me and I'll post it myself.
Okay. cool.
But yeah, I think we put the last one up pretty quick. But yeah, if we don't, for some reason, if one of us gets busy, yeah, just email me, I'll do it myself.
Thank you.
Yep. Yeah, like we were saying in the manometer problem where you could disregard that initial pressure, you can't do that here because we're starting with a pressurized tank where this PA actually has substantial, very substantial pressure. It's 200 kilopascals. So we're going to determine the resulting force acting on the plates B, C, and CD caused by the water. The tank has a width of 1.75 meters. All right. So for BC, we're going to find, since this is a horizontal plate, we're just finding the pressure at B because pressure at B and C would be the same thing. But the really important thing to realize here is remember that pressure always acts normal to whatever surface it's touching. So even if it's submerged and going against gravity, it's still pushing like vertically in this case. And then you get the idea. So the calculations and everything are exactly the same, but let's say, if this was actually a really heavy gate that was hinged right here, this would be the force that would be pushing it open. So that's really the most important part about this whole problem is getting you to realize that just because it's against gravity, doesn't matter, pressure is this force acts normal to whatever surface it's touching. So let's get going. So recall P of I equals your initial overpressure plus rho GH. And so in this case, PB equals PC equals PA plus, okay, we already had SI, plus 1,000 times 9.81 times our height, which is 2 meters. Cool. And so I actually didn't do the math for this one, but this is the same exact calculations as before, so I'm just gonna skip straight to the pressure and string everything together, or straight to the force and skip, do that. So equals P, I'll call PBC times area, which is equal to 200 times 10 to the third pascals plus 1,000 times 9.81 times 2, all in brackets, times the area, which is 1.25 times 1.75 wide. Cool. So now, for the force acting on this, if someone wants to do that math for me, I do have the answer to it. So it's on my phone. Ha. Nice. But yeah, I mean, even if I did mess up a number here somewhere, this is literally the exact same thing as all you've been doing. It's just realizing the force goes in the opposite direction. So, at any rate, you guys don't have to do it. I'll just say equals some number. But in the negative y direction, because it's acting up in negative y direction. Cool. So, hey, did anyone do that math quick? Somebody have it fast? If not, no big deal. It's cool.
I got 480,000-ish.
Sure. Yeah, sounds about right. Said 480-ish? Yeah. KPA.
Yeah.
Sure. Sounds about right. Or that would be newtons. Sorry. So kilonewtons. In negative y direction, which sounds about right. Obviously I don't know the number off the dome, but that seems about right. Yeah, okay. Now for the force acting on CD, it's the same thing, except we're caring about the height of the centroid in this case. So this would be 0.75 plus 2, so 2.75 below. So I'll say F on CD equals the pressure, which is our 200 10 to the third plus 1,000 times 9.81 times 2.75 bracket times the surface 1.5 times 1.75 wide. And yeah, same thing, also just same math. So FCD equals some number again, but now this is just our normal, it's acting in this direction, so if we want to call that X and Y, this would be in plus X direction. Cool. So that's that. Any questions with that? This one was pretty basic, but yeah, the important things to note is you can't always, if this was open to atmosphere and we're talking in terms of gauge pressure, you could just ignore this P0 term, but since we specifically stated that it has an overpressure, you can't ignore it. So you have to use this PA to calculate everything else. So that makes it a little tougher. But yeah, and another important point to note is on a submerged object, the pressure is always acting normal to whatever surface it's touching. So here, we'll be pushing up instead of side or whatever. So,
For 1.25 times 1.75, that area, what is that area? That's just, like, I don't know what area that's representing.
it's this area right here. Because this is 1.25 wide by 1.75 meters into the page. It's just the surface that's of this little wall. Like imagine this is projected out like this.
Oh, okay.
Yeah. And obviously that's the actual profile of the tank or whatever. So it's 1.75 meters wide. Whatever. It's just that surface pushing on. It's just the thing about this too, we always draw stuff in 2D and you have to imagine them in 3D. I wish we would just print things out in 3D because we have good printers and stuff. But, whatever. Anyway, all right. Any more questions? All right. If you have any questions, come see me in my office hours or any of the other professors or TA's office hours. Anyway, yeah. Thank you. All right. Get it now. Cool.